Welcome to this demonstration video. This is a piece of work that we're doing on behalf of the World Federation of Haemophilia. In particular, it's on behalf of the Laboratory Sciences Committee. My name's Steve Kitchen. I'm a laboratory scientist, currently a member of the Laboratory Sciences Committee. The chair of the committee is Dr. Sukesh Nair from Vellore, India. He's also had some input into this piece of work. We'll be demonstrating some methods and techniques that are described in some detail in our laboratory manual. I'm very pleased that this manual is available for free. It can be downloaded either as a single document, the full manual, or in fact in individual sections. We've set it up now on the website so that it's possible to select an individual method. So it's available on the World Federation of Haemophilia website. I think you know the address, www.wfh.org. And of course you also know that WFH is an international organisation, and so I'm also very pleased that we have available the manual in a number of different translations. It's available again through the website in Spanish, in French, Arabic, Russian and Chinese. So everything that we'll be talking about is described in some detail in the laboratory manual. So there are some important components of the inhibitor assay. Probably the single most important reagent is the source of factor VIII that we will use in the test. There have been a number of versions of the factor VIII inhibitor assay available to us for a number of years now, and historically the most widely used techniques have used plasma, pooled normal plasma, as a source of factor VIII. Historically, a number of centres used factor VIII concentrate, and if it's a concentrate that's used in the assay, then it's essentially an Oxford assay. Not widely used. The most frequent currently used assays employ plasma as a source of factor VIII. And in fact, the recommendations in the WFH laboratory manual, for example, and elsewhere, national guidelines, recommend use of pooled normal plasma as a source of factor VIII. For many years, the assay that was used was the conventional BETHESDA assay, described originally in the mid-70s, Carol Casper and colleagues. And this was used for many years, but people became aware that there were some issues with this assay, and it's subsequently improved. And so the current recommendations from ISTH, SSC, and again also in the WFH laboratory manual, are to use a modification of the BETHESDA assay. And the modification was described by colleagues in the Netherlands, in NIJMEGEN, and the name of the assay, NIJMEGEN modification of the BETHESDA assay. So this is the recommended technique to use. So how does this differ? How is the BETHESDA constructed, and what's in the NIJMEGEN modification? Both the NIJMEGEN and the original BETHESDA, again, use pooled normal plasma as a source of factor VIII. The difference is that the NIJMEGEN modification recognised and described the importance of buffering the factor VIII. Buffering so that the factor VIII is protected. If we place plasma, including factor VIII, in a water bath at 37, we will progressively lose factor VIII over time from that plasma. It will happen by breakdown, by degradation, even in the absence of inhibitor or antibody. If we buffer the factor VIII, this protects the factor VIII better during that period, so that the loss is much slower in the absence of added inhibitor or the presence of inhibitor. So if we don't have inhibitor or antibody present, we still lose factor VIII, but that loss is much slower if we buffer the factor VIII to protect it. The detail of the NIJMEGEN modification, the technique for buffering, involves addition of a imidazole buffer to the plasma. And that's been carefully demonstrated in the publications. Actually, there are a number of ways to buffer pooled normal plasma, and it's highly likely that many of these other methods of buffering provide similar protection. And so I think the important thing is to use a plasma which has been buffered in some way. So if we incubate pooled normal plasma in a water bath at 37, there will be some minor loss of factor VIII. What we need to know in order to look for the presence of an antibody in a patient sample is whether or not adding that patient sample, with or without antibody, when we add that to pooled normal plasma and incubate in the water bath, do we see additional loss of factor VIII over and above the amount of factor VIII that would be lost simply by natural degradation? If we've got additional loss, it's caused by the presence of antibody inhibitor. And so this is the principle of the technique. We need some way to control for the loss of factor VIII over that incubation, since, as we've mentioned, there is some loss in the absence of antibody. So we need a control to control for this non-antibody related loss. So one of the important components of the assay is a control mixture. In the original Bethesda assay, the control mixture was an equal volume of pooled normal plasma mixed with assay buffer. Could be Auron's buffer, could be imidazole buffer, the buffer that's used in factor VIII assays. So 1 part pooled normal plasma, 1 part buffer. That's the original Bethesda. The NIJMEGEN modification also recognized, introduced a second change. First change, the pooled normal plasma is buffered. Second difference, second change, when that controlled mixture is constructed, it's a mixture of pooled normal plasma, not with buffer, but now instead with factor VIII deficient plasma. And you can imagine that this makes the control mixture more similar to the patient mixtures. Patient samples are not buffer, patient samples are very frequently severe haemophilia patient samples. So again, very similar to factor VIII deficient plasma. So we need a source of pooled normal plasma. And this can be, a number of materials can be used. Some centres prepare this locally as a pooled normal plasma, pooling citrated plasmas from healthy normal subjects, and that's acceptable. If this is done, then it's important to buffer this preparation for the reasons we've mentioned. We've got a method described in the laboratory manual, the WFH laboratory manual, in which that buffering is performed using a Heapes buffer. And the recipe and details are all, again, in the manual. I'd refer you to that. So that can be used. If that's prepared locally, then it can be stored in aliquots deep frozen. If so, it should be stored at an adequate temperature. -20 freezers, in particular domestic grade -20 freezers, absolutely unacceptable. Very frequently these will have automatic defrost cycles, the temperature of the plasma will raise, there'll be partial thawing, and this can really compromise the plasma that's stored in this way. So it's really important that the pooled normal plasma, if it's deep frozen, should be stored at a sufficiently low temperature. -35 will be adequate for at least 3 months, could be as much as 6. -50, -70, -80, then we'll get stability for at least 2 years, and of course that's an important advantage. We don't need to make the pool quite so frequently. So frozen local plasma is acceptable, it should be buffered. Many centres are currently using an alternative source of buffered normal plasma. Many centres use the pooled normal plasma that's available to them already commercially and being used in, for example, factor VIII assays. When we calibrate a factor VIII assay, we use a reference plasma. Very frequently, most frequently, a commercial material. It's been lyophilized, reconstituted for use, of course. But those commercial plasmas are also carefully buffered. Not usually buffered with the exact regime that's recommended in the NIJMEGEN modification, but nevertheless buffered for a similar reason, to protect the factor VIII, to introduce more stability once the sample is reconstituted. And again, many centres are using these successfully in factor VIII inhibitor assays, so I think there are a number of options. So we have, just now for the assay we're about to perform, some pooled normal plasma, buffered pooled normal plasma. In order to construct a control material, a control mix, we need a source also of factor VIII deficient plasma. And that can be, usually is, the same factor VIII deficient plasma which is used in factor VIII assays. However, there is an absolutely essential feature, and that is that we need to have a normal concentration of von Willebrand factor present in the factor VIII deficient plasma. There are a number of studies which have shown the results which we obtain in factor VIII inhibitor assays are influenced by the presence or absence of VWF in the factor VIII deficient plasma. So I think it's important that that's present in this particular setting. The other features that are important for the factor VIII deficient plasma would be the same ones relevant to a factor VIII assay. So in other words, it must be completely deficient in factor VIII, less than 1 international unit per deciliter, less than 0.01 international units per mil if you prefer. It should completely lack factor VIII. It's absolutely essential, of course, that it does not contain any inhibitor. We know that many factor VIII deficient plasmas, commercially available factor VIII deficient plasmas, many of these are constructed from normal plasma by immunodepletion. The manufacturer uses an anti-factor VIII antibody to remove factor VIII from normal plasma. This is a typical mechanism for creating factor VIII deficient plasma. And there have been reports that rarely the antibody used has found its way into the final material, so that the factor VIII deficient plasma contains some residual inhibitor. And this is completely inappropriate for use either in a factor VIII assay or what we're now discussing in a factor VIII inhibitor assay. I think that would be obvious. So should absolutely no inhibitor presence important. The other feature, of course, is the deficient plasma should contain normal concentrations of the other clotting factors relevant to a factor VIII assay. At the end, as you'll see, at the end of the inhibitor assay, we need to make a factor VIII assay. So the factor VIII deficient plasma, particularly there, should have normal concentrations of the other relevant clotting factors, contact factors, factor 12, 11, 9, 10, 5, prothrombin, fibrinogen. So that's the factor VIII deficient plasma. We have a test sample that we'll be using to demonstrate the assay. Just as for any other assay in hemostasis, we need some evidence. We need some evidence that the factor VIII, that the assay has been successful. And where do we get this? We get this most importantly from our quality control sample. It's really important to include a QC sample, a sample for which we know the level of inhibitor in advance. This should be included in the assay, and only if we obtain a result within our expected target, only if this occurs, can we safely release the test results for patient management purposes, just the same as for every other test. We did a survey of centres performing factor VIII inhibitor assays through one of our proficiency testing programs, and we noticed that a number of centres were not at that time including an IQC material, and I think that's a bad mistake in my opinion. It's absolutely essential to do so. So we have a QC sample. So we'll be preparing a series of mixtures, a control mixture, pooled normal plasma with factor VIII deficient plasma, an IQC mixture, the same pooled normal plasma with some of the IQC material, and some test plasma mixtures. Test plasma plus the same pooled normal plasma. So there are a number of things we need to think about when we are selecting dilutions to construct this assay. There are a number of things we need to keep in mind. In particular, we need to think, what is the level of inhibitor that we anticipate in the test sample? Sometimes we have some information that gives some clue about this. Often we don't. Sometimes when we're performing an VIII inhibitor assay, it's to confirm what we believe and anticipate that actually no antibody is present. Perhaps it's a screen as recommended in a number of guidelines. It's a check prior to important surgery, for example. So we may not expect to find an inhibitor in such a sample, but we need to confirm that it's not present. We may be monitoring a patient who we know to have an inhibitor in the past, perhaps a patient who's undergoing immune tolerance induction, or perhaps a patient where we want to check the level prior to a procedure in order to inform clinical decisions about which products should be considered. So sometimes we know some information in advance, and that we should take into account when we construct the assay. It will save us some time. So if we anticipate the patient does not have an inhibitor, perhaps it's again a check before surgery, then in this setting we would normally test the patient sample without prior dilution. We simply mix the patient sample with pooled normal plasma. If we think the patient may have an inhibitor 1, 2, 3, 5 units per mil, then we should make several different patient and pooled normal plasma mixtures, several different mixtures. And in each of those mixtures, we use the patient sample at different concentrations of inhibitor, different concentrations, different plasma dilutions. So we make some dilution before we mix with pooled normal plasma. So the test sample I have that we're about to use, this test sample has a grossly prolonged APTT. It's about 140 seconds on this sample. For a method with an upper limit of normal of around 38, 39 seconds, a gross prolongation. On that sample, we did a second APTT reagent, and the prolonged APTT, once again, grossly prolonged, actually about 100 seconds with the second reagent. And this is typical of patients with severe haemophilia, with or without inhibitors. Gross prolongation, a little bit different by different methods. We also did a mixture with one of those APTTs. We did patient sample mixed with an equal volume of pooled normal plasma, a 50% mixture, and we did an APTT on this with one of those reagents. The reagent which gave 140 seconds, on that mixture was around 45, 50 seconds, so still prolonged on an immediate mix without incubation, suggesting the presence of an inhibitor. And so we're suspicious that there may be an inhibitor present in this sample. So how will we take that into account? It may be negative. I don't expect that, but in case it's negative, in case it's absent, we will make a mixture to incubate of the patient's sample which has not been diluted. But since we're suspicious there may be an antibody present, we'll make several pre-dilutions of the test sample. So I'll make a dilution 1 in 2, I'll make a dilution 1 in 4, I'll make a dilution 1 in 8. And each of those will mix with same volume, pooled normal plasma, and incubate. So we'll prepare those mixtures. The dilution material, the diluent, to make pre-dilutions of the test sample, this should be whichever is the diluent used routinely in the factor VIII assay. Could be imidazole, glyoxylene, could be aurans. Critical, pH 7.35. The same assay buffer as used in factor VIII assays. So this is used for pre-dilutions of the test sample. The QC material is something which we include with each group of assays. So we've assayed this on many occasions. So we know from past results what the anticipated result should be, and we're using this to confirm that the assay's been successful. And so for our particular QC, this particular lot number, this is run in our assay with a dilution of pre-dilution 1 in 20. So I also need to construct this. Again, that dilution made in factor VIII assay buffer, so the QC and patient samples treated in the same way. So we need to construct these. So for the IQC material, we will make a 1 in 20 dilution from our buffer. So for convenience, 1.9 mils of buffer, .1 mils of QC. So 1 in 20 pre-dilution. just to take the antibody concentration down to an appropriate level. And mix. So this is our control material. This is our patient sample. Suspicious of inhibitor, grossly prolonged APTT, fails to correct. So to make a 1 in 8 dilution, (700 microliters of buffer, and in a moment 100 microliters of patient sample. To make a 1 in 4 dilution, (300 microliters buffer, to which we'll add in a moment 100 microliter of patient sample. And for the 1 in 2, I'm going to make also a 1 in 2 dilution, 200 microliters of buffer, to which I will add in a moment now 200 microliters of patient sample. So this is a 1 in 2 dilution. Remember, 300, 700, 100 of patient to each. So we have some patient undiluted, neat plasma not yet diluted. We have patient diluted 1 in 2, 1 in 4, 1 in 8. Control and patient mixtures should be an equal volume of pooled normal plasma, equal volume of 0% factor VIII for the patient, equal volume pooled normal plasma, equal volume dilution of patient. We should have the same volumes in each. We're trying to reproduce in the patient mixtures as closely as possible what we've done with the control mix. So we need to have sufficient volume at the end of the incubation. We need sufficient volume to perform some factor VIII assays, because at the end of the incubation we will ask ourselves an important question. How much factor VIII is lost from the patient mixtures? Is it the same as the minor loss in the control mix, or is there additional loss? Additional loss caused by antibody. So we need to make some comparisons of the levels of factor VIII remaining at the end of the incubation in the patient mixtures relative to the control mix. So we need enough material on completion of the incubation, enough material to perform some factor VIII assays. Since we'll be doing that today in the manual method for the purposes of illustration in the water bath, I'm going to need around about 300 microliters to make that test at the end. So I'm going to make a mixture just now to be sure I've got 400 microliters to use later. So 400 microliters in total, equal volume of pooled normal plasma and factor VIII deficient. So 200 microliters of factor VIII deficient plasma. That's here. That's going to be used for the control mixture. At the moment, nothing else in this tube. We're going to add the pooled normal plasma in a moment, but first I want to prepare the volumes of control, IQC, and patient. So control mix, factor VIII deficient plasma, 200 microliters. Internal quality control sample, remember it's pre-diluted, 200 microliters, awaiting pooled normal plasma. Patient sample, the test, undiluted, 200 microliters, test sample, not diluted. Patient sample with a pre-dilution now of 1 in 2, 200 microliters. Most important, obvious, but most important to label the tubes. I already did this. Very important so that you know which mixture is where. Patient sample diluted 1 in 4, 200 microliters. Nothing in the tubes yet, just the deficient plasma, IQC, patient sample. Final mixture, 200 microlitres of patient diluted 1 in 8. Final tube. So no factor 8 added yet. The tubes which are used for incubation are important. This should be a plastic tube, something which we know will not have any influence on the coagulation process during this incubation period. So something which doesn't particularly drive contact activation, for example. So standard plastic tubing that we use in other areas of hemostasis testing. So at the moment, no added factor 8. So we now have our source of factor 8. Could have been a frozen pool, as mentioned. Could be a reconstituted commercial source. That's what I'm using just now. Most important that the volume of this added to each tube, therefore the factor 8 added, is exactly the same in each tube. So I'm about to make 6 mixers, each one with 200 microlitres. So I need 1200 microlitres. So what I should not do is reconstitute or thaw 2 separate 1 ml vials, use one of those for some additions and the other one for the other. Even though I anticipate those vials should be identical, let's make sure that the material is absolutely identical. Therefore, I already pooled those different vials together here before this process. So I'm confident that the same factor 8 will go into each of these as long as I accurately pipette. So 200 microlitres into each. And since we're commenting on the accuracy of pipettes, it's really important that there are regular checks on pipette calibration and actions taken to improve where there are problems of precision. And we've got some of that described in the laboratory manual. So each of these should be mixed. So now we've got the same amount of factor 8 in each of these tubes. And these should be capped, for example, with film, as in this case. So each of the tubes capped and then incubated. This incubation is best done in a water bath. It can be done in a dry incubator, and it may be in future that this is done on autoanalyzers. And that can be done. The important thing is that it's maintained at 37 degrees during this incubation period. And absolutely important that the control mix and other mixtures are exposed to the same conditions. So they all go together into the water bath. Water bath is useful because you get efficient heat transfer. So it comes to temperature very quickly and maintains that temperature constantly. So these will now be incubated in the water bath. So as soon as this mixture is made and placed in at 37, if there is antibody present, it will begin the process of binding and neutralizing factor 8. It's a slow, time-dependent process, typically. The binding and loss is not usually linear over the whole period of the 2-hour incubation. It's progressive over that time, and there are different phases. It means that we absolutely have to control exactly the incubation time. And the recommendation in the Bethesda and in the NIJMEGEN modification, the recommendation is 2 hours, and this should be timed. So I need to make a record of the start time. And carefully controlled. It's absolutely essential that we come back to these tubes at 2 hours. And when we come back to those tubes at 2 hours, we need to have available and ready to move straight into assaying the reagents for a factor 8 assay. Really important. We don't want any delay at the 2 hours because there will continue to be additional loss of factor 8 if antibody is present. That loss will continue beyond 2 hours. So if there's some reason why we can't make the assay then, and it's 2 hours, 10 minutes, 20 minutes, 30 minutes, we can't do it. We'll get potentially an overestimation of the real antibody concentration. It is possible to, let's say, stop that process of antibody binding and neutralization by dropping the temperature up, by putting the mixtures immediately onto melting ice. but it's absolutely not recommended in my opinion. I think we're much better not to do that. Let's go straight to the factor VIII assay and get the best possible information we can get. So we need to keep a record of what we've done. I think it's important to use some kind of written evidence, and this is, for example, is the sheet that is used in my centre. So we've got here the source of normal plasma. We've called it standard here, but it's the source of pooled normal plasma and its lot number, batch number or lot number. We've also got here the batch or lot number of factor VIII deficient plasma. We know that manufacturers make changes from time to time. For example, there have been changes in some manufacturers' deficient plasma where the level of von Willebrand factor is improved. And so we need to keep records of lot numbers so that we can check back to see whether there's any influence of a change over such a lot number change. The person who did the test and the date of the test. And you can also see a number of boxes here. When we come to make the factor VIII assay at the end of this incubation, you'll see that we will use multiple dilutions, so we have the opportunity to store that information. For now, we should record the dilution of QC material that we've used, the lot number of QC, so this is recorded on this sheet, so we know which dilution we used. The printed form said 1 in 10. Actually, that was the previous lot number of IQC. The current lot number has a little higher antibody concentration, so we need to make a higher dilution. Why do we need to do that? Why is that important? It's essential because the more antibody that's present in the patient sample, or the IQC, the more antibody that's present, the greater will be the loss of factor VIII over that 2 hours. More antibody, more destruction, more loss. A lower level of residual factor VIII. But what's been shown by careful study is that the assay is fully quantitative provided the residual factor VIII at the end of the 2-hour incubation. It's quantitative provided the level of factor VIII in that incubated mixture is somewhere close to 50% of its starting point. And I'm now using the term percent advisedly. I do not mean percentage where it's used sometimes interchangeably, inappropriately with international units per deciliter. We're talking about the residual factor VIII in the patient mixtures relative to the control mixture, where we take the control mixture as our 100% point of reference. Whatever remains in the control mixture, we consider 100% residual. It's not exactly the same place it started. It usually drops a little during the 2 hours. It's not 100 international units per deciliter. Remember what went into that control mixture. Half factor VIII deficient, nothing in it, no factor VIII. Half pooled normal plasma. Pooled normal plasma might be 90 international units per deciliter, might be 100 international units per deciliter, might be 105, somewhere close to 100. So that control mixture begins somewhere around at half that level. So somewhere around 50 international units per deciliter. Might be 40, 45, 50. It's not critical as long as it's fairly close to that value. The key is that we want to know in the patient mixtures, have we lost any extra? How much do they contain relative to the control? We don't need the absolute factor VIII concentration, only the relative concentrations. Has it lost extra factor VIII? Therefore, we work in percentage. What is the percentage in the patient mix? Percentage relative to the control. So we know that the assay works extremely well if the level of inhibitor leaves somewhere around 50% residual factor VIII relative to control. And so we really want to construct our initial dilutions in order to create something which will leave somewhere around 50% residual factor VIII. And in that respect, we have an international definition to help us. The international definition, 1 Bethesda unit NIJMEGEN, BETHESDA the same. One BETHESDA unit of factor VIII inhibitor destroys, inhibits, 50% of the added factor VIII in 2 hours at 37. We're incubating for 2 hours. So if the test, or IQC, if it contains 1 unit per mil, 1 BETHESDA unit, we will have, by definition, 50% residual activity. And we noticed, others have noticed, it's been reported that the assay works particularly well when residual factor VIII in the end of the incubation is somewhere close to 50%. And that's the purpose of constructing these several different pre-dilutions of the test sample. We're trying to create in one of those pre-dilutions an inhibitor concentration somewhere close to 1 BETHESDA unit per mil, so that the residual factor VIII will be somewhere close to 50%. You'll see when we make the plot how we fully quantitate the assay. And again, it's described in some detail in the WFH lab manual. So if the residual factor VIII at the end of 2 hours, if it's close to 100%, it means there has been no additional loss. No antibodies present. 100% residual, 0 inhibitor. This is a factor VIII assay we'll be performing. We know that factor VIII assays are subject to some assay variability. It's not possible to remove that. So if the true level is exactly the same as the control mix, if it truly is 100% of the control mix, when we make the assay, we might get 100% or 95 or 105 or somewhere close to 100, because we know the assay is little variable. So if the residual factor VIII lies between 90%, 110%, we're confident there's been no change relative to the control mix. 0 antibody, negative. We know if the residual factor VIII is below 75, 70%, below this kind of level, we're pretty confident that actually that number truly is different from 100. We really have lost something. But if we get a figure of 85, 88%, how confident are we? Well, then I think we're in a grey area where it's not clear, because we know the assay is subject to variability. And for this reason, there is an agreed threshold of sensitivity. And we'll talk about that in some detail when we come to plot the results. So it's very important to control the incubation period, to time this exactly. And so these tubes are now exactly on 2 hours. They've spent 2 hours in the water bath. Control mixture, pooled normal plasma, factor VIII deficient plasma, no antibody. IQC mixture, same pooled normal plasma, a dilution of the IQC material, and then a series of mixtures. Test the same test sample at different dilutions, incubated with pooled normal plasma. So the question now, have we lost any extra factor VIII? Any extra in the patient mix relative to the loss in the control mix? So the first thing we need to do is to remove all of these tubes together from the 37 degrees water bath, and these are now held at room temperature during the period of assay. So we have a control mixture, IQC, patient sample not diluted, neat plasma, patient sample diluted 1 in 2 before constructing the mix, patient sample 1 in 4 before the mix, patient sample 1 in 8 before the mix. So we need to check the levels of factor VIII now in each of the mixtures relative to the control mix. So we can use the control mix to construct a calibration line in the factor VIII assay. This is an equal mix. Half pooled normal, contains around 90 to 100 international units per deciliter. Half factor VIII deficient, completely lacks factor VIII, so has around 40 to 50 international units per deciliter factor VIII at the beginning of the 2 hours, some minor loss during that 2 hours. If we were making a full factor VIII assay, and this were a calibration plasma containing close to 100, we might, for example, use 1 in 10, 1 in 20, 1 in 40 dilution. This contains approximately half that concentration as we've mentioned. We need to take that into account in constructing the further dilutions for the factor VIII assay. So I'm now going to make dilutions 1 in 5, 1 in 10, 1 in 20. So not so diluted as the full factor VIII assay might have been. So 1 in 5, 1 in 10, 1 in 20. These dilutions are constructed with the same assay buffer as used for factor VIII assays. If that's imidazole glyoxylene in the centre for the reagents, that's what should be used here. If it's Auron's buffer, that should be used here. We're using Auron's buffer just now. The plastic tubes to construct the dilutions, these should be the same that would be used for a factor VIII assay. We're working in the water bath just now because we want to illustrate the principles. Of course, these factor VIII assays just now would be very frequently performed on autoanalyzers, and that's perfectly acceptable. There's some advantages to that, improved precision and so on, faster processing, all advantages. But it's perfectly acceptable to perform this test in a water bath for patient management purposes. The precision is good enough, and I think we're lucky in hemostasis testing that that's true, that we're able to do this without expensive equipment. So we start with the control mix. In the plastic tubes, 1 in 5, 1 in 10, 1 in 20. So these contain 400 microlitres of dilution buffer to make a 1 in 5, 900 microlitres to make a 1 in 10, 1.9 mils to make a 1 in 20. So we'll now add 100 microlitres of the control mix to each of those tubes. And each one is mixed. This is used to construct the calibration line. So we need to treat this as though it were a standard now in a factor VIII assay. So 3 disposable glass tubes. These should not be reused. Some centres have tried to use reused tubes by washing. I absolutely recommend against doing that. It's very difficult to do this in a way that really removes all the clot, the factors, and all the detergent used for washing. So it's absolutely false economy in my opinion. It introduces many problems. So single-use glass tubes. In the water bath, I already have a tube containing APTT reagent and a tube containing calcium chloride. And these are exactly the same APTT and calcium concentrations, exactly the same ones as used in factor VIII assays. And since we'll be performing a series of factor VIII assays, one on each of these mixtures, we need to think in advance which is how many assays, how many tubes, which is the volume of factor VIII deficient plasma, and to be sure we have a single pool of the factor VIII deficient plasma for use during this assay. So this contains a mix of 2 or 3 vials of 1 ml, so that this is pooled before starting. So factor VIII deficient plasma. Really important that this contains 1 millibrand factor. This can have an important effect on the results of factor VIII inhibitor testing. So for each of the 3 glass tubes, 100 microlitres factor VIII deficient plasma. Simply warming up to temperature at the moment. Fresh pipette tip. Control mix. Diluted 1 in 5, 100 microlitres. First tube. Control mix, diluted 1 in 10, 100 microlitres, second tube. Control mix, 1 in 20, guess what, third tube. Just warming up to temperature. And mix. APTT reagent, warmed to 37, to the first tube, start the watch, 3-minute activation for this particular APTT reagent. Second tube, (15 seconds) and mix. Third tube, (30 seconds) and mix. So we've added APTT reagent, activator, phospholipid. Contact activation is now occurring, 12 to 12A, 11 to 11A. We don't have essentially any calcium present, so at this moment we're simply activating. In 3 minutes, just as we did for the one-stage factor VIII assay, just as we would do for an APTT, add the calcium, record the endpoint. The APTT reagent that's used here should be the same one, can be the same one which is used for factor VIII assays. It is useful at this point to make the assay with an APTT reagent largely unaffected by lupus anticoagulant. It has happened, it's not a rare occurrence for patients with, for example, acquired haemophilia, may have multiple antibodies present. Sometimes we've certainly seen patients with both acquired haemophilia, anti-factor VIII antibodies, and in addition, antiphospholipid, lupus anticoagulant. So they can occur together in the same patient. And if we've got lupus anticoagulant present, that could have an impact on the results and clotting times during this assay. And therefore, there is some advantage to using an insensitive reagent, so a reagent with a very high phospholipid concentration. This will minimize the impact of lupus as an interfering substance. Of course, we're performing just now a factor VIII assay. And as you know, there are alternatives to one-stage factor VIII assays, alternative versions of factor VIII. It can be assayed in chromogenic assays, for example. There are a number available. And there are some studies which have looked carefully at the results of factor VIII inhibitor testing to compare use of chromogenic techniques with one-stage assays for determination of residual factor VIII at this point. And in congenital patients, there is, in most cases, good agreement, but it's very clear that there can be some big differences between the inhibitor titers if we use chromogenic assays in patients with acquired haemophilia. So I think we need more data on this before we can make a firm conclusion about whether it's safe to use chromogenic assay in this setting. So 3-minute activation, calcium to the first tube, start a stopwatch, 15 seconds, calcium to the second tube, start a stopwatch, 30 seconds, calcium to the third tube, start a stopwatch. Now we need to observe these mixtures for clot formation. And so now we have a balance between maintaining the temperature of the incubation mix whilst the tubes are immersed, but at the same time we also want to observe in order to record the clotting time. So the recommendation is that this tilting should be 3 times every 5 seconds through an angle of 90 degrees. And that's what I'm now trying to do. So we have a clot in the first tube. Second tube, of course, contains a higher dilution, therefore less factor VIII, and therefore a longer clotting time. Just waiting for the third tube to clot. Lowest level of factor VIII, longest clotting time. So we've now got a clot in all 3 tubes. The nature of the clot is really quite obvious. It's a solid structure at least it is for most of the clotting times. If we have a very prolonged clotting time at this stage, up to the 120, 130, 140 seconds, then it can be a much weaker endpoint. But even then, I think it's clear that a clot has occurred. So we need to record the clotting times. So for the first 1 in 5 dilution, 63 seconds. For the 1 in 10 dilution, 69.5 seconds. And for the 1 in 20 dilution, 76.2. So later we'll be using those clotting times to construct a calibration line on the graph paper. We'll come to that a little bit later. So that's the control mix. We now need to do the same for the internal QC, IQC sample. So again, just the same, 3 glass test tubes, 1 for each dilution that we're about to prepare. So we've now got the IQC sample. So remember, this mixture was 200 microlitres pooled normal plasma, 200 microlitres IQC sample. The IQC sample was diluted 1 in 20 before we made the mix. It's to take account of the expected level in this sample. That's based on our previous results on this IQC material. So we know that the IQC material contains antibody, contains anti-factor VIII, so we expect that there will have been loss of factor VIII, additional loss from this mixture relative to the control. That's what we'll now check. So this material, just as the control mixture was, 1 in 5, 1 in 10, 1 in 20, same dilution buffer, the buffer that's used for factor VIII assays, and mix. So we make a set of dilutions and test, obtain the clotting times, move to the next tube, make a set of dilutions and test. We should not make all the dilutions, test the first, test the second, test the third. It introduces additional variability. So we're trying to treat each of these materials the same as the control mix. 3 glass tubes, factor VIII deficient plasma, 100 microlitres in each tube. Trying to reproduce here the same conditions as we used for the control mix. Warm to 37. First tube, 1 in 5. Second tube. One in 10. Third tube, 1 in 20. So we'll be treating this now and all of these other mixtures in the same way. In turn, make the dilutions 5, 10, 20. Add to factor VIII deficient plasma. Warm to temperature. Activate with APTT reagent, 3 minutes for this reagent. Clot with calcium, record the clotting times. We need to convert the clotting times into percentage residual factor VIII. And we're going to make a comparison between the IQC and the test sample mixtures and the control mixture. We're interested in the loss of factor VIII from the QC and test mixtures relative to the control mix. So we can use the control mixture as our calibration material for the purposes of this calculation. So we're not now working in international units per deciliter, we're looking at the relative concentration. So the 3 dilutions of the control mix, 1 in 5, 1 in 10, 1 in 20. We ran a control mix, effectively a calibration material, both at the beginning and at the end of the assay, with all the IQC and patient mixtures assayed in between those two standard control mixtures. And that's so that we know whether the assay conditions have stayed constant over the period of assay. We want to first ask the question, rather like we did for factor VIII assays, are the clotting times in the standard control mix at the end of the assay, are the clotting times similar to those which we obtained at the beginning? So if we start with the 1 in 5 dilution, we obtained a clotting time of 63 seconds at the beginning of the assay, and at the end, 62. Very similar. These times should be within 5%. These are close enough. So we need to take that clotting time to the graph paper. The graph can be plotted using log paper. That's what we're now using. We notice that this gives good lines, usually, for the reagents that we've been using for this demonstration. It could just as easily, for many reagent sets, it could be plotted using log linear scale. This also frequently gives a good line, good calibration line. So we're using log just now. So we have the horizontal axis with a scale where we plot the concentration or dilution. So if we take the first one as 100%, then the other gradations, 90%, 80, 70, 60, 50, 40, 30, 20, 10%, 9876, 1%. Coming back to our assay dilutions. On this occasion, in this factor VIII inhibitor assay, the first dilution we used was 1 in 5, and it's conventional to take that first dilution and plot that in the 100% position, whether it's 1 in 5, another assay, different reagents might be 1 in 10 for the first. Either way, we consider the first dilution 100%. In this case, 1 in 5, 100%. 62 seconds, 63 seconds. We plot the clotting time on the vertical axis. If the first one is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, this is log scale, 200, 300 and so on. So this is the clotting time in seconds. 62, 63, 62 and a half, the average clotting time. Here on the 100% line, 62 and a half. Now we consider the second dilution, 1 in 10 dilution. First dilution 1 in 5, next dilution 1 in 10. So what's the relative concentration? 5 over 10 times 100, 50%. So we plot the 1 in 10 dilution here at the 50% line. Clotting times for the standard control mix, 69.5, 69. Same time, more or less, average 69, 69.5. Just under 70 seconds. Third dilution, 1 in 20. First dilution 1 in 5, so what's the relative concentration? 5 over 20 times 100, 25%. 1 in 20 dilution. Clotting times, 76.2, 77.5. Very similar. Average clotting time, 77. Is this a straight line relationship, for which we need the ruler? Do we have a straight line between joining the 3 points? Yes, it's a straight line. It's not perfect, but the points are very close to this, so we've got a line of best fit, straight line relationship. So we can proceed. QC material. Before we can move to any patient samples or patient results, we need to ask the question, have we obtained the correct answer? Has the assay worked? And this comes from the IQC material. 1 in 5, 1 in 10, 1 in 20. Clotting times, 71 seconds for the 1 in 5 dilution, plotted on the 100% line. Second dilution, 1 in 10, plotted on the 50% line, therefore, 78 seconds. Here. Third dilution, 1 in 20, 25% line, 89 seconds. Here. Do we have a straight line relationship? And is it parallel to the standard? We need to meet both criteria for the assay to be valid. So we're looking for a line of best fit. Is it parallel to the standard? Straight line relationship, yes. Every point exactly on the line, no. Some small differences, half a second, that's typical. Straight line relationship, yes. Parallel to the standard, yes. We've got a valid assay. We need to ask the question, in this IQC material, what's the concentration of factor VIII here relative to the control mix? And we do that by looking for the point where the line of best fit, where does that cut the 100% line? And that's here, on or close to that first point. In this case, just below, around 71 seconds. And then we ask the question, what's the concentration of standard which would clot in 71 seconds? And the simplest way to do this is to take a cross here and then to drop a perpendicular here. 46%. It means the residual factor VIII is 46%. We're not working in international units per deciliter. We don't need to. We're not now making any adjustment for the level of factor VIII in the control mix. We don't need to. We simply want to know what have we lost in the QC and test mixtures relative to the control. So we'll leave this in percentage. IQC, 46% of the standard. Now remember that the international definition of one Bethesda unit is that amount of inhibitor antibody which destroys 50% of the added factor VIII in 2 hours at 37. Remember, we incubated 2 hours at 37. Destroys 50%, residual factor VIII, 50%. So if that figure were 50%, it would be a concentration of one Bethesda unit. We need to set these assays up in such a way that the residual factor VIII at the end of the assay is somewhere close to 50%. So on this occasion, 46%, very close. So we will later be able to use that to successfully quantify inhibitor in the QC sample. And we'll come to that in a moment. First, we need to calculate the percentage residual factor VIII for each of the test mixtures. We made 4 different mixtures of patient test with pooled normal plasma. 4 different mixtures. The first one contained patient plasma which had not been diluted, undiluted plasma. And these were the clotting times. For the 1 in 5, 87.5. So here. For the 1 in 10, 94.9. Here. For the 1 in 20, 104 seconds. Here. So for that first mixture of patient with pooled normal plasma, is it a straight line relationship? And is that parallel to standard? So we've more or less, it's not a perfect line, but we've got more or less a straight line relationship, parallel to the standard. Not every point is on the line. Perhaps 1 or 2 seconds here, also 1 or 2 seconds here. That's typical of the assay. Straight line relationship, parallel to standard. Where does it cut the 100% line? In this case, 84 seconds. It means the residual factor VIII in this mixture is around 13%, 13% of the control mix. We know the assay has limitations. One of the limitations is that the relationship between residual factor VIII and inhibitor theta is not linear across a full range of inhibitor concentrations. In fact, we know that we can obtain good information, good data, if the residual factor VIII lies somewhere between 25% residual and around 65, 70, 75% residual. Below 25, and publications tell us, we risk significantly underestimating the real concentration. And we really need to have residual factor VIIIs much closer to 50% in order to obtain a quantitative answer. So on this occasion, for the patient sample undiluted, 13%, significantly below that figure of 25. We know we've lost a lot of factor VIII. We already know that inhibitor is present. Clearly there's quite a strong inhibitor. Majority of the added factor VIII's been destroyed. But we can't use that 13% to reach a conclusion about the concentration. It's in that area below 25. So we need to move on and look at the data we obtained from the other mixtures. So in the next mixture, the patient sample, the test material, was diluted 1:2 before we mixed with pooled normal plasma, 1:2. We made the mix, we've got the clotting times. So the 1:5 dilution, 77 seconds. Here, the 1:10 dilution, 81. Here, and the 1:20 dilution, 90.7, 91 seconds. So here. So now we want to know, do we have a straight line relationship parallel to the standard? What will be the line of best fit? Once again, it's not a perfect line, fairly typical of inhibitor assays. Line of best fit, parallel to the standard. Not every point is exactly on the line. Where does the line of best fit cut the 100% line? Here. So we go across to the standard. From here, drop a perpendicular. Residual factor VIII, 30%. Above 25, it's possible to make a quantitative calculation from this figure, which we'll do in a moment. Next dilution of patient sample. Pre-diluted 1:4, mixed with pooled normal plasma. Clotting times, 70 seconds. 76. 83. So, line of best fit. So with a straight line relationship, once again, not every point exactly on the line. Where does it cut the 100%? Here. What's the concentration of standard, which would clot at this time? Actually, it's absolutely on 50% residual. Final patient dilution, diluted 1:8. Clotting times, 65, 72, 78, 78.5, here. Line of best fit. Across to the standard line. Drop a perpendicular. It's around 85, 86% residual. It's above that critical level of 65, 70. Above this, we can't make use of that figure to draw any safe conclusions about inhibitor concentration. So we can't use the 85%. We can't use the 13%. So that leaves us two results. The 1:2 dilution, 30% residual. The 1:4 dilution, 50% residual. So we need now to convert those residual factor VIII's into inhibitor concentration. To convert the residual factor VIII into a Bethesda inhibitor concentration, we need log linear graph paper, and that's what we have here. On the logarithmic scale, on the vertical axis, we have the residual factor VIII. 100%, 90, 80, 70, 60 and so on. 50%, 40, 30, 20, 10. Residual factor VIII. And then on the x-axis, we have the inhibitor concentration. 0.1, 0.2, 0.3 and so on. And we have two known pieces of information. The first one, if we have no loss of factor VIII, 100% residual, there is no inhibitor present. Zero inhibitor, 100% residual factor VIII, and that's here. That's this point. Zero inhibitor, 100% factor VIII. So this is a given. We have a second piece of information which comes from the international definition. 1 unit per mil, one Bethesda unit per mil factor VIII inhibitor destroys 50% of the added factor VIII in 2 hours at 37. Destroys 50%, residual 50%. So we know that 50% residual here is equal to 1 Bethesda unit per mil. These are the two pieces of information. And we use that with a straight line in this way. So this piece of information has not yet used anything experimental. This is simply from the definitions. So this we can construct anytime. We only need to do this once. We can use this to convert residual factor VIII into Bethesda inhibitor concentrations tomorrow, next week, and that's fine. Turning to our QC sample. The residual factor VIII, 46%. Where is 46 on this line? And the answer is here. It means the concentration of inhibitor in this mix is 1.1 Bethesda units per mil. In that mix. How did we construct that mixture? We made a dilution of the QC material 1 in 20. So the inhibitor concentration in that sample is 1.1 multiplied by 20, 22 Bethesda units per mil. So our first question, what did we expect for this? And the anticipated range, the target range in my laboratory for this particular sample is from 14 Bethesda units to 25. That's quite a wide range. And that's to take account of the variability in the assay. It's an indication of the degree of imprecision which can occur. Is that result inside the range? Yes. It means the assay has been successful. It means we can safely release the patient results for patient management purposes. Turning to the patient sample. When we tested this without pre-dilution, undiluted, 13% residual, it's below the limit, below that critical figure of 25, which could safely be converted to inhibitor. We can't use it. Second patient dilution, the one which was pre-diluted 1 in 2, 30% residual. We come to the graph. Where is 30% residual? Here. What is the concentration of inhibitor that would be associated with 30% residual factor VIII? 1.7. That sample was pre-diluted 1 in 2. So the concentration in the patient, 1.7 multiplied by 2, 3.4 Bethesda units per mil. Next patient dilution. We pre-diluted 1 in 4, more dilute. We've taken the antibody concentration lower. The residual factor VIII, 50%. I don't need the graph. 50% from the international definition, 1 unit per mil. So that contains 1 unit per mil, 1 Bethesda unit per mil, multiplied by 4 for dilution, 4.0. So for those two dilutions, we have not obtained identical answers, 3.4, 4.0. And in my experience, that kind of variability is rather typical of the assay. And I think there are two approaches. Some centres will say, I will take the dilution in which the residual is closest to 50. There's no doubt the accuracy of the assay is better in that area. So some centres would take the 50% and report this as 4 Bethesda units per mil. Actually, in my own centre, we take the view that we get additional information, and I think usable information. So in my centre, we take the average. Any of those residual factor VIIIs in that range 25 to 70, we use those and we take an average. So in my centre, we would report this as 3.7, an average of the two results. Of course, the clinical management decision is really unaffected by that part of the decision. If we report as 4.0, if we report as 3.7, that's the same management decision for that patient. And I think it's something we have to accept from inhibitor assays, that this type of variability will occur. If this were a patient with acquired haemophilia, what we notice is fairly typically we don't recover similar final estimates of antibody concentration from different dilutions. Actually quite the reverse. It's often the case for samples from patients with acquired haemophilia, it's often the case that the higher the dilution before constructing the mixtures, the higher that dilution, the higher is the ultimate estimate of inhibitor concentration. And this can be very difficult. It means that if we're monitoring change response to therapy, for example, in a patient with acquired haemophilia, it's really important to reproduce carefully those same dilutions. So if we produce an answer from a dilution here of 1 in 4, if we want to look for whether or not there's been a change, we should once again test a 1 in 4 dilution. If that's increasing, that's an evidence that the antibody overall is increasing. If it's reducing, that could be evidence that therapy is beginning to be successful. So that's, I think, an important thing to keep in mind. The test sample which we assayed just now, this was from a patient with severe haemophilia outside of treatment, so with no factor VIII in the test sample. Sometimes we want to make this assay, frequently we want to make this assay in a sample in which there is factor VIII present before we move into the inhibitor test. And this has an important implication and has an influence on our assay. We need to take the level of factor VIII into account. And there are 3 ways that this can be done. If the patient sample contains factor VIII, when we make the equal mix, patient with pooled normal plasma, some factor VIII is provided by the patient sample. Not the case here, but would have been so if there were factor VIII present in the patient sample. So the starting point in that mixture is higher, the level of factor VIII is higher than the level in the control mix, equal part same pooled normal, but with a completely deficient plasma. In this setting, a higher level in the starting mixture. So we can take that into account when we calculate the residual. That's one possibility, and the mechanism to do this is described in the WFH laboratory manual. That's one possibility. Another possibility is to make an adjustment in the control mixture. So if we know that the patient has a starting level of, let's say, 40 international units per deciliter factor VIII, and we know that the pooled normal plasma we're using has a starting level of, say, 100 international units per deciliter, that mixture will have 140% of the level in the control mix. So we could adjust the control mix, the ratio of pooled normal plasma to factor VIII deficient, to a similar level. That's possible, and that's also described in the laboratory manual. But increasingly what centres are doing in this setting, and I think this might be the best approach, is to heat the patient sample, subject the patient sample to heating before constructing these mixtures. And the way that's done is to put the patient sample at 56 degrees for a period of time. It denatures the factor VIII but does not denature IgG antibody. This is stable under those conditions, though the anti-factor VIII antibody is unaffected. If that antibody were bound to any factor VIII, perhaps during immune tolerance induction, for example, then the factor VIII bound will be removed, will be degraded, and that antibody will be released. Sometimes that's a useful measure to do. So it's possible to do this by heating the plasma. The temperature used is 56 in studies. The period of incubation, some studies have used 30 minutes, others have recommended 90 minutes. For sure 90 minutes ensures absolutely full degradation. In my own experience, 30 minutes actually takes the factor VIII really, really low and may well be sufficient, and of course allows us to proceed with the assay a little quicker. So we can use any of these approaches, but probably this mechanism of destruction by heat treatment, I think, is increasingly the favoured option. All of the techniques that we've described and that we've demonstrated are described in some detail in the WFH laboratory manual, and so again I'd like to refer you to that. It's available as a free download. We've used the manual method in the water bath, and I hope you can see that we're able to obtain good results, that it can be used for patient management, Of course, it may be an advantage to use an automated system. We can improve the precision, but either is perfectly acceptable.